Swayam Prabha. Digital India. Educated India.
So, welcome to the 6th lecture on time forecasting. In this lecture, I will discuss different methods for obtaining the seasonal indices, and I will also discuss the variate difference method, with the help of which you can estimate the variance of the random component. In the last lecture, we have discussed different graphs which represent the seasonal component, or which help you in visualizing the nature of the seasonal component. Once you visualize the seasonal component and once you know that the seasonality is present in the data, it is important to obtain some measures or some indices of the seasonal variations. So, this is the main objective of this lecture. So, determination of seasonal indices. The first method which I have considered is the simple averages method. The steps for this method are: first you arrange the data season wise, then you compute the seasonal averages for each year. So, suppose it is quarterly data and the data is for 2011, 2012, 2013 and 2014. Then you compute averages of all the seasons for each year, is all the quarters for 2011, 2012, etc. Then average of seasonal averages is calculated using the formula grand average equal to total seasonal averages upon number of years. And then seasonal average for each year is divided by the corresponding grand average and expressed in percentages to obtain final seasonal indices. So, this is how you get the seasonal indices using this procedure. Now, we consider a simple example. The example is given here. You have quarterly data for the years 2011, 12, 13, 14 and 15. 5 years quarterly data you have, and then your objective is to find the seasonal indices using simple averages method. If you consider the seasonal plot for this data set, then the seasonal plot is given here. And from the seasonal plot, it is very clear that the observations have seasonal behavior. The observations have an increasing pattern in the quarter 3 for all the years. The observations have some kind of periodicity also. To obtain the seasonal indices, we arrange the data year and quarter wise. So, corresponding to 2011, we arrange the observations of different quarters. 2012, we arrange the observations of different quarters, and so on. Then first we obtain the seasonal totals. So, we add all these observations and the final figure is 316. So, actually 316 is equal to 54 plus 46 plus 65 plus 82 plus 69. Similarly, you obtain seasonal totals for quarter 2, 3 and 4 also. Then we divide these seasonal totals by number of years, which is 5 in this case, and then you obtain the seasonal averages 63.2 141.4, 221.2 and 21.8. Then we calculate the grand average for all the quarters, which is 63.2 plus 141.4 plus 221.2 plus 21.8 divided by 4, and finally you obtain 111.9. So, this figure gives you the grand average. Now, we express the seasonal averages as the percentage of grand average. For example, for quarter 1, we take the seasonal average 63.2, multiply it by 100 and divide it by the grand average, and you get the final figure 56.48. Similarly, you can calculate the seasonal indices for the second, third and fourth quarter also. And if you add all these seasonal indices for the 4 quarters, then summation is 400. Similarly, you can obtain seasonal indices for the monthly data also. For the monthly data, you have 12 months, instead of quarters, you have 12 months. Then you have to calculate seasonal totals for each of the month, and then you can calculate the seasonal averages and seasonal indices. For monthly data, the summation of seasonal indices, final seasonal indices will be 1200. The second method is ratio to moving average method. Basically, we assume that the model is a multiplicative model. So, first we obtain a 12 month. For monthly data, suppose you have monthly data, then you obtain 12 MA means moving average of period 12, or if you have quarterly data, then you obtain 4 MA means moving average of period 4 of the original time series observations. Then to center the values, we further obtain a 2 MA means a moving average of period 2. Then we express each original data value as a percentage of the corresponding centered moving average value found in step 2. So, you have original observations. After taking the moving averages, the values which you will obtain are your trend values. So, you divide the original observations by trend values, multiply it by 100 to express the figures in percentage. And if you are assuming a multiplicative model, then your time series is expressed as T into C into S into I. You divide it by T into C and express it in percentage. So, you multiply it by 100. So, you get S into I into 100. So, trend and cyclical variations are eliminated. Then you arrange the percentages obtained in step 3 according to months or quarters of the given years. Then we further find the averages over all months or quarters of the given years. And then you multiply the averages obtained in step 5 by a correction factor, which is 1200 upon sum of monthly indices or 400 upon sum of quarterly indices to obtain the seasonal indices. Once you apply this correction factor, then For monthly data, the sum of all seasonal indices becomes 1200, or for quarterly data, the sum of all seasonal indices becomes 400. So, to explain this method, let us consider this example. We have quarterly data of rainfall in millimeter of a city for then find seasonal indices using the ratio to moving average method. Now, we arrange the observations according to different years and different quarters. So, you have observations for year 2011, and here you take different quarters, then 2012 different quarters, and so on. And these are the observations. Since you have quarterly data, so first you take a moving average of period 4. So, this column gives you the moving totals, means 399 is the total of first 4 observations, 54 plus 134 plus 179 plus 32. Similarly, you can obtain 391 and so on. Then we obtain a moving total of period 2, means 790 is actually 399 plus 391, and you write the figure in the middle. Then 391 plus 375 is equal to 766. So, you write 766 here, and so on. You proceed like this, and then we obtain the moving averages by dividing each of these totals by 8. So, you get these moving averages. Then we obtain YT upon moving average into 100. The observation corresponding to 98.75, the value of YT is 179. So, actually this figure is equal to 179 divided by 98.75 into 100. So, this is how you obtain the entries of this column. Now, we arrange the entries of last column, this column, like this, year wise and quarter wise. So, we start from here 181.27, 33.42 and so on. Then we obtain averages for each quarter. So, average of 47 and 60.05, average of 118.59 and 132.42. So, you write the averages here. To obtain the final indices, the correction factor is 400 divided by, you take sum of all these values, sum of all these averages, and finally, you obtain 1.003. So, you multiply each of these values by 1.003 and then you get the final seasonal indices. And the sum of all these final seasonal indices is 400, you can easily verify it. Then trend elimination by fitting mathematical curve. The method is very similar to ratio to moving average method. But instead of moving averages, means in the previous method we have obtained the trend values using the moving averages. Now, we use the method of mathematical curve fitting for obtaining the trend values. So, instead of using the moving average values, fitting of mathematical curve is used to estimate trend values. Rest of the steps are exactly the same. Next method is method of link relatives. Now, in this method, first we compute the link relatives for time t as y t upon y t minus 1 into 100. So, we divide each observation by the previous observation and then we express it in percentages, or you can say that each observation is expressed as percentage of previous observation. Then we compute the average of the link relatives for the period S. This S may be month or S may be the quarter, for all the years using mean or median, say AS. For the monthly data, S varies from 1 to 12, for the quarterly data, S varies from 1 to 4. Then we convert the average link relatives into chain relatives, CS. So, first we assume that the chain relative for S equal to 1, that is C1 is 100, and then chain relative for the period S is CS equal to AS CS minus 1 upon 100. So, once you assume that C1 is 100, then you can compute CS for all other values of S. Then we convert the chain relatives CS to trend corrected indices. So, CS dash is the trend corrected indices, which is equal to CS minus S minus 1 into B, where B is equal to 1 upon capital S. This capital S is equal to 4 for the quarterly data and capital S is equal to 12 for the monthly data, into A1 into CS upon 100 minus 100. Again we obtain the adjusted seasonal indices. So, suppose G is the grand total of all CS dash, then the adjusted seasonal indices are given by the formula CS dash into S into 100 upon G. Now, we explain the method of link relatives for obtaining the seasonal indices by this example. Again, we are using the same example which we have used for the earlier procedure. We have quarterly rainfall data for 3 years. Then we arrange the observations year wise and quarter wise, and then we calculate the link relatives. So, the link relative for the first observation corresponding to the first observation is 100. Then corresponding to the second observation, it is 134 upon the previous observation is 54 into 100. So, this finally gives you 248.14. Similarly, you can obtain the other link relatives. So, this table actually shows the link relatives calculated using the formula for linked relatives. Then we take averages. We take average of linked relatives for the first quarter, which is 261.81. The average of linked relatives for the second quarter is 242.58. The average of linked relatives for the third quarter is 152.69, and the average for the fourth quarter is 11.66. Then we calculate the chain relatives using this formula. CS is equal to AS into CS minus 1 upon 100. So, for the first quarter, we fix C1 equal to 100, then C2 again turns out to be 242.58. For C3, AS is equal to 152.69. We multiply it by CS minus 1, which is 242.58, and divide it by 100. So, finally, you get 370.40. Similarly, we obtain the fourth figure 43.19. Then we calculate the value of B, which is correction for the, which provides you the correction for the trend using the corresponding formula, and we calculate the trend corrected indices. So, this row actually gives you the trend corrected indices. Finally, we obtain the adjusted seasonal indices since you have quarterly data. So, you have to adjust it so that all the sum of all the indices becomes 400. So, we use this formula, divide CS dash by the grand total and multiply it by 400, and you get the final figures. For the determination of cyclical component, one can use the periodogram analysis. I will discuss this topic during my lecture on frequency domain analysis. So, right now I am leaving this topic, determination of cyclical component. Then there are some measures for measuring the strength of trend and seasonality. How much strong your trend component is or how much strong your seasonality is. So, for the strongly trended data, variation of seasonality adjusted series should be much greater than that of remainder component. Means the variance of UT divided by variance of TT plus UT should be relatively small. For data with little or no trend, variance of UT will be approximately equal to variance of TT plus UT. Then we define the strength of trend as Ft equal to maximum of 0 1 minus variance of UT upon variance of TT plus UT. So, this figure gives you the strength of trend. Similarly, once you have detrended your data, you have removed the trend component, you can define the strength of seasonality also, which is equal to maximum of 0 and 1 minus variance of UT upon variance of ST plus UT. So, for comparing the trend and seasonality and identifying the series with maximum trend or maximum from a large collection of time series, means you have a large collection of time series and you want to identify the time series which has maximum trend, then you can use these measures. Now, the random or irregular component, it actually denotes the unexplained part of the model. The model has two parts. One is predictable systematic part, which is consist of trend, seasonal and cyclical variations, and then you also have irregular component, which is a random variable, and this is the component which actually makes y t a random variable. So, it may be considered as the unexplained residual part of the time series after eliminating trend, seasonal and cyclic components. Then investigating the probability properties of the random component, particularly estimation of its variance, is important for the statistical comparison, testing of hypothesis, etc. So, we are actually interested in estimating the variance of random component, and for that purpose we use the variate difference method. We assume that the time series is consist of two parts, the systematic part of smooth shape and nearly continuous curve in time r t, and random component u t. So, this r t is the systematic part and u t is the random part. The seasonal and cyclical components are either removed or not very dominant in r t. We assume that these two components have been removed. We can approximate r t by a polynomial of degree q in t. Now, we define some of the operators. Forward shift operator is defined as E y t is equal to y t plus 1 or E j y t is equal to y t plus j. Then difference operator delta y t is equal to y t plus 1 minus y t. It is related with the forward shift operator also by the relation E minus 1 y t is equal to delta y t. Similarly, you may define delta r y t, which is the rth difference, and you can write it as summation j equal to 0 to r c j y t plus j. Then we also define backward shift or lag operator b y t is equal to y t minus 1, b j y t is y t minus j, and del y t is equal to y t minus y t minus 1, which is also equal to 1 minus b y t. So, in fact, this backward shift operator may be considered as the inverse of forward shift operator. Now, since you have approximated r t by a polynomial of degree q in t, if we take q plus 1 differences of y t, delta q r t, this is approximately equal to constant, and delta q plus 1 r t is approximately equal to 0. So, after taking q plus 1 differences, it becomes 0, and after taking q differences, it becomes a constant. So, we take q differences of y t, delta q y t is equal to some constant k plus delta q u t, and then you can write delta q u t in this form. Then we have already assumed that the variances of u t are sigma square u for all t. Expectation of u square t plus j is equal to sigma square u for all t and j, and expectation of u t plus j u t plus L is equal to 0 for all j not equal to L. Now, you can easily obtain the variance of delta y t, which is equal to expectation of summation j equal to 1 to q, q c j u t plus j whole square. Then suppose you have any sequence summation x j So, then the square of this can be written as summation x j square. Then you have cross product terms, summation over j, summation over L, j is not equal to L, x j, x L. So, we use the same formula here. So, we get this term. Now, if you take expectation, then expectation of this term becomes 0 for j not equal to L. So, this term vanishes, and expectation of u t plus j square is equal to sigma square u. So, finally, you get sigma square u summation j equal to 0 to q, q c j square. And this is a simple mathematical problem. Summation j equal to 0 to q, q c j square is equal to 2 q c q. So, this is the final expression for variance of delta q y t. Now, you can unbiasedly estimate sigma square u by using this formula. एक करेक्शन होगा, यहाँ स्क्वायर लगेगा. सिग्मा हेड स्क्वायर यू क्यू इज इक्वल टू 1/2 q c q n minus q summation t equal to 1 to n minus q delta q y t whole square. Why you are dividing by n minus q? Because in this summation you have n minus q terms. So, obviously, if you take expectation of the right hand side, then using this final result, you easily obtain that the estimator, this estimator or this right hand side provides you an unbiased estimator of sigma square u. Now, in practice, what we do? We calculate the estimator of sigma square u corresponding to different values of r, means corresponding to different differences for r equal to 1 to so on. So, you have calculated sigma head square u 1 based on the first difference, sigma head square u 2 and so on. And we stop when this sigma head square u r stabilizes. So, this is how you can estimate the variance of random component. Now, we consider the effect of elimination of trend on other components. Once you eliminate the trend component from the time series, how is it going to affect the seasonal component or random component? So, we express the time series y t as t t plus c t plus u t. T t is the trend component, C t is the oscillatory component and U t is the random component. And suppose operator f is used to completely eliminate the trend component, so that f y t is equal to T t. So, y t minus f y t is equal to C t minus f c t plus U t minus f u t. So, you have used the operator f for calculating the trend component and for eliminating the trend component, you have to subtract f y t from y t. So, naturally, it is going to affect the cyclical variations and irregular variations also. So, the problem is how f c t and f u t are going to distort the oscillatory moment and random component. Now, first we consider the effect on the oscillatory moment. So, suppose f is the k term moving average and C t is equal to a sin 2 pi t upon lambda plus phi. So, the oscillatory moment has amplitude a, lambda is the time period and phi is the phase angle. Then f c t is the k term moving average of C t, or 1 upon k a summation t equal to 1 to k sin 2 pi t upon lambda plus phi, and if you add this sine series, then finally you obtain a into g sin pi k plus 1 upon lambda plus phi. So, the original amplitude was a, now the amplitude of new series after taking the k term moving average is a g, where g is equal to sin pi k upon lambda upon k sin pi upon lambda. So, f c t is a sine wave with same period of oscillation remains the same and same phase of the oscillation is also not affected, but amplitude multiplied by g, and g is this factor. Now, suppose k upon lambda is large or k is a multiple of lambda. So, if k is a multiple of lambda, then this term becomes 0, sin of pi k upon lambda becomes 0, and this makes f c t approximately equal to 0. So, in this case, the moving average has no effect on the oscillatory moments. So, the moving average does not affect your periodic component or periodic variations. If moving average is repeated say m times, then the amplitude is multiplied by g to the power m. Now, if time period lambda is large, that is your oscillations are very slow, that is k upon lambda is small, then in that case g is approximately equal to 1. So, in that case f c t is approximately equal to a sin pi k plus 1 upon lambda plus phi, amplitude has not changed. So, this moving average is going to affect, or it is going to have a severe effect on the cyclical variations. So, by taking moving average, slow moving oscillations will be eliminated as trend. If the time series has slow moving oscillatory component, then it is eliminated, because the moving average treats the slow moving oscillation as trend. Then moving averages highlights shorter oscillations at the cost of longer ones. Shorter oscillations are highlighted and longer oscillations get eliminated. If G is negative, means FCT is negative. The trend eliminated series CT minus FCT may have more intensive oscillations than the original series. So, this may also happen. In comparison to your the original series, the series which you have obtained after eliminating the trend component has more intensive oscillations. Now, we consider the effect on random component. This is also called Slutsky-Yule effect. Again, we assume that UT follows UT has mean 0 and variance sigma square u, and we apply moving average of period k. So, f ut is equal to say Vt, then Vt is obtained by taking k period moving average of ut. So, V1 is the average of u1, u2, so on uk. V2 is the average of u2, u3, uk plus 1 and so on. Sigma square V, you know, if since V1 is the average of k terms, its variance is equal to 1 upon variance of V1 is equal to 1 upon k into variance of u. So, sigma square V is equal to sigma square u upon k, which is less than sigma square u. So, the variance of random component after taking the moving average reduces. The random variations or irregular variations become more smooth. Then we obtain the covariance between V1 and V2. This is V1, this is V2. We obtain the covariance between V1 and V2. So, you multiply V1 and V2 and take expectation. Then the terms like U1, U2, U1, U3, so on U1, UK have expectation 0. The only terms which have expectation non-zero are U2 square, U3 square and so on UK square. So, k minus 1 terms have expectation sigma square u, all other terms have expectation 0. So, ultimately covariance of V1, V2 is equal to k minus 1 upon k sigma square u, and then this is equal to, you can write it as 1 minus 1 upon k sigma square u. In general, if you take the covariance between Vt and Vt plus s, then this is equal to 1 minus s upon k sigma square u for all s between 0 to k, and for s greater than or equal to k, you get no terms common. So, you get covariance between Vt and Vt plus s equal to 0. From here you can easily obtain the correlation coefficient between Vt and Vt plus s, which is given by rho Vt, Vt plus s. So, you know that the original random component series ut does not have any dependency structure. We already assumed that uts are identically independently distributed. So, the correlation between any two terms of uts is 0, but after taking the moving average transformation, means the transform series, the transform series is this Vt, and different terms of this transformed series are correlated. So, this series Vt has a dependency structure. So, this is how the k-term moving average affects the random component or random series. The original random series does not have any dependency structure, but after taking the moving average, the resulting series has dependency structure. Further, the transform series has lower variance than the original series. So, the transform series is naturally smoother than the original series. So, these are the two main effects of taking a moving average on the random component series ut. The terms become correlated with each other and the series becomes smoother than the original random series. Then moving averages and the seasonal component. Now, suppose the time series has a seasonal component with S seasons, and we apply a moving average of period S. Then what happens? It covers all the season periods. For example, if you have monthly data, then S is equal to 12, then 12 period moving average covers all the months. So, the moving average series will eliminate the seasonal effect. It is going to completely eliminate the seasonal effect. The resulting moving average series will be a seasonally adjusted series. It does not have any seasonal component. That is why for the determination of seasonal component we have also used the method of moving averages. If the period of moving average is a multiple of S, in that case also it eliminates the seasonal effect completely. So, just to conclude, today we have considered different methods for obtaining the seasonal indices. For means you can use different graphs which I explained in one of my earlier lectures for obtaining for the visualizing the seasonal component, but to obtain the seasonal indices or the magnitude of seasonal indices, you have to use all these methods. You can use the variate difference method for estimating the variance of random component or irregular variations. In fact, usually we are not so much interested in magnitude of the random component, but we require estimate of its variance for many testing of hypothesis or for comparing different series, etc. Then we have also considered the effect of elimination of trend component by using the method of moving averages on cyclical and seasonal variations as well as the irregular variations. That is it. Thank you.
Hi, I'm Chitwan Lalji, a PhD student of Health Economics under the supervision of Dr. Debayan Pakrashi from the Department of Humanities and Social Sciences, IIT Kanpur. In one of my essays, I'm interested in understanding the relationship between consumption of fruits and vegetables and various health indicators. Health indicators, both subjective and objective health indicators like mental health, self-assessed health, various measures of blood pressure and various measures of cholesterol. Measures of blood pressure like systolic and diastolic BP, you have your incidence of high BP, MAP and incidence of high MAP. And as far as cholesterol is concerned, I have tried to concentrate more on total cholesterol, good cholesterol and incidence of high cholesterol. Now before I go on to what have been my major contributions and various policy implications, I would like to briefly tell you about the policy initiatives of WHO and various countries. The WHO, that is the World Health Organization, it started with a campaign of 5 a day. That is, you should have 5 portions of fruits and vegetables per day. That would be approximately, you could say, 400 grams of fruits and vegetables. Now, a portion, before we go further, I'll just tell you what exactly is a portion. One portion is equivalent to a medium-sized apple, or one small glass of fruit juice, which is approximately 150 milliliters, and maybe 3 teaspoons of vegetables. So, the WHO went with a 5 a day campaign, which was further taken up by various countries. Countries like UK, Netherlands, Germany, Norway, they adopted the 5 a day policy, while some went for expansionary dietary policies like France, Australia, Canada, Denmark. So, for example, Australia, it went for 2+5 policy, in which it said that you should consume 2 portions of fruits and 5 portions of vegetables per day. And USA went for a policy of fruits and vegetables more matters. That is, you must consume more and more fruits and vegetables. Now, irrespective of these expansionary dietary policies and dietary propagations, it has been found that only 28% of women and 25% of men, they actually meet the recommended dietary norms of 5 a day portion. So, the major contribution of my work is firstly to find an association between fruits and vegetables, whether there exists a relationship between fruits and vegetables and health indicators, and if they exist, whether due to heterogeneity in the data. So, I will be doing it according to age, by gender and by your weight. So, apart from that, I will go for policy recommendations, in which I am basically studying how much fruits and vegetables matter. Apart from that, which type matters more. So, for that I have taken data from the Health Survey of England. Health Survey of England is an annual survey which takes data, which conducts information regularly on demographic and socioeconomic characteristics. You have your lifestyle behaviors like an individual smokes or doesn't smoke, alcohol consumption, you have your sedentary and physical activities, and you have various health indicators also which have been collected. Before I go on to what exactly is my research, I would like to concentrate more on fruits and vegetables, like what kind of questions were asked in the survey. Questions like, what kind of fresh fruit do you eat? Did you eat any dried fruit yesterday? Don't count dried fruits in cereals, cakes. Apart from that, for vegetables, they asked how many tablespoons of vegetables did you eat yesterday. So, approximately after this whole survey was conducted, data was converted into portions of fruits, and like for example, 3 tablespoons of vegetables is equivalent to 1 portion. So, data was converted and provided to the users, that is us, from the UK Data Health Survey. So, the major contributions of my paper is that I found a strong negative association between intake of fruits and self-assessed health, then various measures of blood pressure like mean arterial pressure, high blood pressure, systolic and diastolic BP, and your total cholesterol. Apart from that, I have found a strong positive association between consumption of vegetables and good cholesterol. So, it is recommended in a way that if you want to control your blood pressure, you must consume more and more fruits, and as far as vegetables are concerned, they impact your good cholesterol. Apart from that, I went in for a falsification test. A falsification test is basically conducted to know whether the model that you have adopted and the conclusions that you are drawing are not spurious. So, if a falsification test is done to know, in a way it is tested by seeing an indicator, a health indicator which is not being impacted by your consumption of fruits and vegetables, and then we see whether there is significant result or not. If there is no significant result, that means your model is good and your results are non-spurious. So what we did is, for falsification test, we took ear complaints and infectious diseases. Now ear complaints, like if you are deaf since birth or you have some kind of imbalance, body imbalance, that is not being impacted by your consumption of fruits and vegetables, and we did find insignificant results. Apart from that, infectious diseases like HIV, AIDS, etc., we found similar insignificant results, indicating that our results are not non-spurious. Apart from that, we went, since there was a lot of heterogeneity in the data, like by gender, by age and by weight, we did the regression analysis. We found results which stated that as far as fruits are concerned, it impacts a male's health more than a female's health. So it is basically said a man should consume more fruits to impact his health, whereas as far as vegetables are concerned, they impact a women's health more. But this has been only seen as far as cholesterol is concerned, the various measures of cholesterol like total cholesterol, good cholesterol and your incidence of getting high cholesterol. Now after this, we went in for a policy implication, and in the policy implication we tried to find two policy implications: what matters and exactly how much portion matters. So as far as how much portion matters, we have found that on an average 5 or more portions of fruits impact your overall health, that is your self-assessed health, your MAP, your incidence of high MAP and incidence of high BP. But if you want to have a good mental health, so you can optimize your mental health by consuming 3 or 4 portions of fruits as well. And similarly, as far as self-assessed health and total cholesterol is concerned, an individual must consume 4 to 5 portions to optimally have the impact of consumption of fruits. Apart from that, vegetables have had a very little impact on your health. It only impacts your incidence of getting high MAP and high BP, and it's seen that only it impacts when you consume 5 or more portions of fruits. So an optimum consumption of 5 or more portions of fruits and vegetables are recommended, but fruits have a more impact on your overall health, on various measures like self-assessed health, mental health, your various measures of blood pressure and various cholesterol levels. Another thing that we find is which type of fruit matters. It has been seen that all size fruits, they impact your self-assessed health, your systolic and diastolic blood pressure, your mean arterial pressure, your high BP and incidence of getting high MAP and high cholesterol. But we find that as far as frozen fruits or canned fruits are concerned, they help in regulating your incidence of getting high MAP or high BP, but it has a trade-off. That means there is something negative happening. It reduces the good cholesterol in your body. Apart from this, if you have an incidence of getting high cholesterol, it is recommended that you must consume fruit juices, because it has a impact in reducing your probability of getting high cholesterol. And dried fruits, they impact your self-assessed health. As far as vegetables are concerned, very little impact has been seen. It has only been seen in case of portion of salads and its association with self-assessed health. Another thing that they have seen is vegetables in composite, they have an association with good cholesterol. So overall, my research basically says that there is an association between consumption of fruits and vegetables and various health indicators, and it is highly recommended that an individual, in order to be healthy, must consume 5 or more portions of fruits and 5 or more portions of vegetables per day, but fruits have a more impact on your overall health. Apart from that, all size fruits, they have a better impact on your overall health, your mental health, various measures of blood pressure and cholesterol. So, thank you.